A rigid tank initially contained 1.4 kg saturated liquid water at 200 degrees Celsius. At this state, 25% of the volume is occupied by the water and the rest by air. Now, heat is supplied to the water until the tank contains saturated vapor only. Determine the volume of the tank, the final temperatures and pressure, the internal energy change of the water. So, first of all, let's take a look at the information given. Here it mentions about the rigid tanks. So, as previous example, for the rigid tank, usually the volume for the state 1 should be equal to volume at the state 2, meaning that there's no change of the volume. And then in this case, they are going to use water as a working fluid. Therefore, I need to use table A4, A5, and A6 in order for me to find the properties of the water. So in this case, we have to state. So let me draw the diagrams. So I will say that this is going to be my state 1. So my state 1 here given T1 equals to 200 degrees Celsius. And then it is in saturated liquid. And then heat is supplied. So now this is going to be processed. And then my thermodynamic system here is going to reach state number 2. And then state number 2 over here, it mentions about the saturated vapor. So the condition should be saturated vapor. So in this case, as I said in the previous example, in order for me to use the steam table, I need to find minimum of 2 different properties. So in this case, I already got 2 for the state 1. State 1 here, I did know that I have a temperatures and also I have the condition which is saturated liquid. Therefore, I need to use for state 1 for the T1 equals to 200 degrees Celsius, and then it is at the saturated liquid. So I'm going to show you how do I get the data. Yeah. So in here is a saturated liquid water, which is table A4. So now I have temperatures of 200, and then I need to find the specific volume is going to be VF, because it was in the saturated liquid. And then I also need to find the internal energy. So now my internal energy is going to be UF. So these two is going to be my state 1 properties. So now I'm going to rewrite my answer in the answer sheet here. From table A4, my specific volume for the state 1 is actually equals to VF at 200 degrees Celsius, which is equals to 0.001157. 0.001157 meter cubes per kg. And then I also have my internal energy for the state 1. U1 is actually equals to UF at 200 degrees Celsius, which is equals to 850.46 kilojoule per kg. So to recap, The reason why I'm using VF and also UF over here is because given in the question is stated that for my state 1 it is actually in the saturated liquids. Saturated liquid usually the data will be UF, HF, VF and SF. So that's why I'm using this value. So if you still cannot understand this, you can refer back to the summary videos which is already uploaded. Yeah. Alright. So now I would like to try to attempt for the first part of the question, yeah, which is the volume of the tanks. So just like previous videos, I do know that the volume at the state 1 was actually equals to specific volume at the state 1 multiplied by M. To recap, this one is actually coming from, I do know that specific volume with the unit of kilogram, with the unit of meter to power of 3 per kg, and then I do know that meter to power of 3 is a unit for volume, kilogram is unit for mass. So I can come up with this equation. Specific volume was actually equals to volume divided by mass. And then if I'm going to get the value of volume, I can just simply multiply by specific volume with the mass. So now I can use this one to find the volume occupied by the water. So here the specific volume, which is from here, equals to 0.001157 multiply with the mass, which is given in the question, 1.4. Then I'm going to get the value of volumes equals to 0.006476 meter cubes. So this one maybe a little bit confusing, yeah, because this one was actually the volume by water. This one is just volume by water because they are talking about the mass of water multiplied by specific volume of water. Therefore, this one is going to be volume of water in tank 1. And then if I would like to calculate for the total volume for the state 1 was actually equals to, because in here it does mentions that at this state 25% of the volume is occupied by water, meaning that this one is actually only 25%. So if I'm going to calculate for the total volume, means that I have to so to explain this one mathematically, I will say that 25% of total volume equals to this value, 0.0676. And then if I would like to find the total volume, means that the total should be 100%. 100% of total volume is going to be, so this one I have to use the multiplication, this one multiplied by this one divided by this one. So now I have 100 multiplied by 0.006476 divided by 25 is actually equals to total volume, which is this one. So this one is just mathematics, yeah. So I should get that the total volume is actually equals to I make mistakes, 1.4. Sorry about that, I make mistake over here. I already calculate before, so when I rewrite it, sometimes I get confused. So this one should be 0.001619. So this one should be 0.001619, and then the total volume should be 0.006476 meter to power of 3. So I hope that you'll be able to understand the concept, yeah, because in the question here, first it does mentions that, so imagine that this is my state 1, so this is the whole total volume, and then but then only 25% or a quarter is occupied by water, while 3/4 is occupied by air. That's why I have to do the simplification, something like this. So now I be able to calculate what is the total volume of my system over here. Alright, I'm going to erase some of the answer here because of the space is not sufficient. Alright, so now I'm going to move on to the second part of the question, which is what is the final temperatures and pressure? Means that the question is actually asking for what is my T2, what is my P2. But then if you notice that we only have one properties over here. We only have saturated vapor only. Therefore, we need another properties so that we can apply the steam table. But then, going back to the question, it does mention about the rigid tanks, means that the volume is going to be the same. And then, because this is a closed system, therefore, there won't be any mass flowing in or out of my system. There won't be any mass flowing in and out. Therefore, the mass here, let's say mass here equals to 1.4. For my second state, or state number 2, the mass is going to be the same. So, since I already got the volume for the state 2, which is already calculated, I have 0.006476 meter cubes, and then I have a mass which is equal to 1.4 kg. So from here, I can calculate for specific volume for state number 2. Specific volume is just simply volume 2 divided by mass, which is 0.006476 divided by 1.4, and then it's going to be equals to 0.004626. But then, if you notice that it's given in the question for the state 2 here, it is actually saturated vapor. So my VF here, which is equals to this value, it is actually equals to my VG. So I need to find what is the value of VG, which is equals to this value, 0.004626. So I have to use a steam table. So to find the saturated vapor, I need to use this column, which is saturated vapor, represented by the symbol VG. So I need to find the value of 0.004626. So here is going to be tricky, because I need to find the information 0.004626. So I have to slowly. So now hold on, 0.004626. Going up here, saturated vapor. because it's given in the question for the state 2, it was actually in the phase of saturated vapor. So I need to use this column. So 0.004626. So most probably somewhere around this area, in between this one and also this one. For 626. 4626. Oh, sorry about that. My mistakes. Let me erase it. So let me rewrite here. Otherwise, it's going to be a little bit confusing. So my V2, my specific volume, equals to 0.0. What happened? Oh gosh. My V2 was actually equals to Vg, which is equals to 0.0046. Is it 64? No, 4626. 4626. So it should be. I want this value. Yeah, saturated vapor value. So 4626 should be located in between these two. Should be located in between 0.003646 and 0.4994. So here, in order for me to get the temperatures and also pressure, I need to use the what we call interpolation. So let me show you one example. Let's say I want to find the temperatures. So now I have let's find the value of pressure, because I'm not going to show all. Let's find the nice number, which is pressure. 21,000. P equals to 21,000, and then the value of Vg equals to 0.004994, and then I have pressure equals to 22,000, and then the value of Vg equals to 0.003644, and then what I want here is my pressure for the Vg equals to 0.004626. So now here, what I can do here, I can do the interpolation. So means that, let's say the value of P here is, let's put it as a P2. So now I just use P2 minus this one, P2 minus 21,000 divided by this one minus this one. So it's going to be 22,000 minus 21,000 equals to, so because at the top here I just minus here and here, therefore I have to minus this one. So it's going to be 0.004626 minus 0.004994 divided by, and again same as above, this one is going to be minus this one. So it's going to be 0.003644 minus 0.004994, and then I just simply solve for P. So by solving for P, I should get the value of 21,367 kilopascal, and then the same methods can be used to apply for the temperatures. Yeah, this is how, because we have to do the interpolation. So once we already complete that one, we actually have to use for the internal energy. Same goes for here. For the internal energy, what I have to do here, I have to do another interpolation, because before this we have done interpolation for pressure, and then we have to redo the interpolation for temperatures, because the temperature data should be here, and then the answer should be in between 369 to 373. My answer should be in between this value. Why? Because my saturated vapor, specific volume for saturated vapor here, the value was in between this value. Therefore, my temperatures also should be between this value. And then I'm getting the value, the answer somewhere around 371.3 degrees Celsius. And then we have to find the U2, which is internal energy. So for the internal energy, because it was in the saturated vapor region, therefore I have to find the UG. So I need to find the value should be in between this value, and then let's say I'm getting something like 2201.5 kilojoule per kg, because I have to do the another interpolation by using the value of VG here and also UG here. So this is how we solve for this type of question, yeah, because we have to solve for the we have to find the interpolation, because sometimes the value, for example, the value here is not a round number. Unless it was a round number, then it should be easier for us to solve it. Otherwise, we have to do some interpolation. Alright, yeah, I think it is done for the question number 1 here. So I'm going to continue with the question number 2, yeah. Usually for my video, I'm going to limit the question for maximum of 3. So for example, for this video, it's going to be only 2 different questions, so that you don't have to spend a lot of time for one video. Alright, let us solve for the question number 2. Yeah? Water initially at 200 kilopascal and 300 degrees Celsius is contained in a piston cylinder device fitted with stops. The water is allowed to cool at room temperature until it exists as a saturated vapor, and then the piston rests on the stop. Then the water continues to cool until the pressure is 100 kilopascal. On a TV diagrams, sketch the respect to the saturation line, the process curve passing through the both initial, intermediate, and final state of the water. Label the T, P, and specific V for the specific value and the end process of the process curve. Find the overall chain of internal energy between initial and final state per unit mass of water. Here I got 3 different states, yeah. So if I'm going to sketch, initially this is going to be my state 1, and then given that at the state 1 here, P1 equals to 200 kilopascal and T1 is going to be 300 degrees Celsius, and then it was contained in the piston cylinder devices fitted with the stop. The water is allowed to cool at constant pressure until it exists as saturated vapor, and then the piston is rest to stop. So here given that saturated vapor, and then because the process here, it does mention in the question, yeah, the process here is actually a constant pressure, therefore the pressure here P2 is going to be the same as P1, which is 200 kilopascal. Alright, then we already reached at the state number 2, and then in between, this one is going to be state number 3, yeah. So between the process between state number 2 and state number 3, then the water continues to cool until the pressure is 100 kilopascal. So now what does it mean is, after it reached at the state 2 here, it's going to be further cool until it reached at the state 3, for which now my pressure is going to be my new pressure P3 is going to be 100 kilopascal. Alright. So if I'm going to explain by using this diagram here, okay, initially it was this state, and then it was the pressure was it was allowed to cool, meaning that once it's allowed to cool, what happened to the piston here is going to be moving down until it reached at the stop here. So now this is going to be my state number 2. See, meaning that the volume is going to be changed, yeah. And then from the state number 2 to state number 3 here, this piston cannot move further down anymore. Why? Because there's a stop over here. So means that here I can say that my specific volume at the state 2 was actually equals to my specific volume at the state 3. Hope you'll be able to understand this one. Yeah? So if I'm going to draw my piston cylinder diagram, it's going to look something like this. Initially, I have a piston, I have a cylinder, and piston look something like this. So this is my initial state. And then at the state number 2 here, because it was allowed to cool down, the piston over here, because I have a stop here, this is my stop. So because it was allowed to cool down, means that the piston over here is going to move down for the cooling process. So now my piston is going to be just above this one. So meaning that it was moving down. So this is going to be my state number 2, and then this one is going to be state number 1. And then what happened to the state number 3? For the state number 3 here, if you notice that because we installed a stop over here, this piston cannot move further down anymore, even though it is a cooling process. So now if I'm going to draw my piston cylinder device, it's going to be look something like this. So from the diagram itself, from these two diagrams, I can conclude that my volume here, V2, is going to be the same as volume here, because because the piston already rests at the stop here. So this is how we're going to explain this type of question. Yeah. So now I'm going to sketch the diagrams. Yeah. First, I have to rectify the condition. So here they give me, so here they give me temperatures 300 degrees Celsius. So by checking the temperatures of 300 degrees Celsius, I should note that my pressure should be 9,209. But then for the saturated liquid, yeah, saturated liquid vapor. So but then my pressure here is only 200. Therefore, I can say that my state 1 here is a superheated. So if I'm going to draw a PV diagram, a T versus V. So because here equation does mention on a TV diagram, sketch with respect to the saturation line. What does saturation line mean? Saturation line means something like this. We just draw randomly. Doesn't look nice, huh? Let me redraw it. In my first video, I did explain how do I come up with the and again, let me redraw it. You don't have to worry much about to draw it accurately, yeah, because this one we just simply sketch. So let me draw it. So the question asking for with to plot PV diagrams. So I have to draw a saturation line, and then this is going to be P equals to 200 kilopascal. And then here I'm going to have P equals to 100 kilopascal. If you still struggling on to how do I get this trend, means that, for example, for the constant pressure, P equals to 200 kilopascal. If you're still struggling, how do I get this trend? You can refer back to the videos title 201, because this one I did explain how do I come up with this diagram. How do I come up with this is what we call saturation line. And then how do I come up with this one? So means that now my state 1 here, let me use a different colors. It was actually located at the superheated steam, pressure of 200, which is here. So I can say that this is going to be my state 1. And then for the state 2, the pressure was actually 200, which is this line. But then it was actually located at the saturated vapor. So this one is going to be my state number 2. And then for my state number 3 here is going to be somewhere around here. This is going to be my state number 3. Why? Because number 1, the pressure was 100 for the state 3. But then I do know that V2 and V3 are the same. See, I did mention that V2 and V3 are the same. Therefore, because the mass also constant, therefore, my specific volume at state 2 was actually equal to my specific volume at the state number 3. Therefore, I can come up with this point. Alright. So, this is how you should draw your TV diagrams, yeah? Alright, the question is actually asking for what is the change of internal energy between initial and final state. So for the initial state, it should be straightforward, yeah, because for the state 1, here I have P equals to 200 kilopascal, and then I have T1 equals to 300 degrees Celsius. So because I already conclude that it was in the superheated region, therefore I have to use table A6. Does it? A4? Yeah, A6. So I need to use table A6, yeah, for pressure equals to 200 kilopascal. Pressure P1 equals to 200 kilopascal, or equals to 0.2 megapascal. So I need to find a column for 0.2 megapascal. Hold on, yeah, 200 kilopascal and 300 degrees Celsius. 0.2. Yeah, here. So my state 1 should be, the data should be somewhere around this column, and then my temperatures is actually 300 degrees Celsius. 300 degrees Celsius, I want to find the information on I. So on U, yeah, therefore my U1 is going to be, U1 equals to 2808.8. So let me rewrite over here. U1 is actually equals to 2808.8 kilojoule per kg. So I already got this one, because what I want here in the question, it does mention that I need to find U3 minus U1. What is the value? So do I need to find the information on the point number 2 here? From the diagram itself, I should note that my specific volume at the point 2 was actually equal to specific volume at the point 1. Point 3. So means that the V here should be the same. Therefore, in order for me to get the value of VF here, the V here, because otherwise my information won't be sufficient, because notice that for the state 3 here, I only have one information. I only have pressure. By knowing only one properties, I cannot really use my steam table. Therefore, I need to find my specific volume at the point 2 here. Then I can use the specific volume at the point 2 to the point 3. So let me write down the answer. Yeah? For the state 2, I have P2 equals to 200 kilopascal, and then my X2, if you remember that X2 here was equals to 1, the steam quality, because it was in the saturated vapor. And then my V specific volume for state 2 was actually equals to, now my variation is pressure, therefore I have to use table A5. My pressure was actually equals to 200, so here, and then my V2, my specific volume is going to be V2 is actually equal to Vg, because it was saturated vapor, equals to 0.88578. 8858. Let's make it my calculation simpler. So now I have V2 equal to 0.8858 meter cubes per kg. So now I already got the information from state 2, and then I can say that at the state 3, say I only have pressure P3 equals to 100. I cannot really use my steam table by using one information only. Therefore, I can say that my specific volume at the state 3 was equals to specific volume at the state 2, which is equals to 0.8858 meter cubes per kg. Then, because I have two properties, therefore, I can solve for the state 3. So, take a look at the table A5. Because obviously it was not in the superheated, so I can say that 8858 for the pressure equals to 100 kilopascal. So this is my pressure for 100 kilopascal. My see, for the 100 kilopascal, I do know that my VF equals to 0.001043, and then for my VG is going to be 1.6941. So I can rewrite over here. I need to erase it, does it? Hopefully. Okay, at 100 kilopascal, my VF is actually equals to, oh gosh, my VF equals to, hold on, my VF equals to 0.001043, 0.001043, and then my VG was actually equals to 0.8578. No, 1.6941. 1.61. But then if you notice that this value was actually in between this value, therefore what I have to do here, I have to find what is the value of steam quality, meaning that X. And then after I get the value of steam quality, I can use to find the U3. So U3 here is just simply equals to, oh, okay, hold on, yeah. So 1.6, hold on, yeah. Somehow my pencil doesn't work. 1.6941. So see here, 1.6941. So now, but then my value of my V3 was actually equals to 0.8858. But then I do know that V3 specific volume at the state 3 equals to VF plus X VFG. But then the X was actually equals to V3 minus VF, V3 this one, minus VF, which is this one, divided by VFG is just equal to VG, which is this one, 1.6941. 0.0041 minus 0.001043. Then I'm going to get the value of x. Once I get the value of x, because if you still remember, we need to find the u3. We need to find the u3 minus u1. u1 should be straightforward, yeah, because we already calculated one. So in order for me to find u3 here, is actually equals to uf plus x ufg. So x actually coming from calculation before, and then uf you can just simply read it from the steam table, because given that the pressure was 100, and then my uf is going to be 417.40, and then plus x, which is calculated before, steam quality, x multiplied by ufg, see, ufg, which is equals to 2088.2. So calculating that one, and then I'm going to put it here. So this one from steam table, and then this one calculated from previous calculation, and then ufg here is just from the steam table calculated before. Yeah, you can try it by yourself. Hopefully this video will be able to help you to have more understanding, yeah. But then we going to upload the textbook together with the solution manual, so that you can try a couple of questions by yourself. I think this is the end of this part of the video. Hopefully I will be able to upload another one video, which is covering on the water as working fluids. Hopefully we'll be able to cover 3 questions, and then most probably one more video on ideal gas equation. That one should be very short video. Thank you.